Okay. So solar cell is also same, but here we are going to convert the sunlight into electrical power. In photovoltaic cell, I'm going to convert it into voltage or current by means of connecting a load or by taking directly the output across the load, right? But in solar cell, when I'm going to make illuminate the device with the sunlight is converted into electrical energy. So it is just like I'm going to have a battery and it is going to provide electrical power. Okay, I'm going to store everything in the battery, and whenever needed, I can take energy from the battery for my purpose. So this solar cell and photovoltaic cell are almost similar in operation, and the working principle, everything is going to be same, except that I'm going to have some property in the form of how the energy is converted from light into voltage or current in the photovoltaic cell, and here I'm going to have the light energy conversion happening into the electrical energy. So you are going to have same structure. You are going to have a PN junction diode. You are going to dope them P type. You are going to dope them with uh, P and N type. You are going to dope them. N type, I'm going to dope them with donor impurities. P type, I'm going to dope them with acceptor impurities. And the basic construction of solar cell is shown here. You can see here the basic construction. You have a P, N, and the metallic contact. And you have a glass plate which is going to focus your incident light on the PN junction diode. Here you are going to make the light incident on the P region, and I'm going to take output across the PN junction diode. Okay, so you can see the construction is shown here, and the sunlight is going to incident on the glass plate, and this glass plate is going to ensure that all the sunlight incident is perfectly focused into the diode. So incident photon will collide with the valence electron and make it move to conduction band. So electrons are there in valence band. So as and when a photon is going to hit your PN junction layer, PN junction diode, the electrons in the valence band will pick up the energy from the photon and they will move to conduction band. So when more number of electrons from valence band move to conduction band, you get what is called as current flow. Okay, you will get current flow happening inside the device. So as a result, an electron hole pair is formed, and newly formed electron minority carriers in the P region. So they freely move across the junction. Similarly, holes are formed in N region, and they cross junction in opposite direction, giving rise to the flow of current. The flow of these electrons and holes are going to be in the direction opposite to the conventional forward current in PN junction diode. So thereby it is going to lead to accumulation of majority carriers on both sides. So you are going to have lot of charge carriers on both sides, which are going to cross the depletion region and give us the current. The total current will be current due to majority carriers plus current due to minority carriers. In P region, the majority carriers are holes and minority carriers are electrons. In N region, the majority carriers are electrons and minority carriers are holes. So you are going to excite the electron to move from valence band to conduction band. So when electron is going to move from valence band to conduction band, the holes will be moving in the reverse direction from conduction band to valence band. And these transitions happen because of photon hitting your PN junction layer. The light is incident on the P region only. So in P region, electrons are minority carriers. So electrons will be moving from valence band to conduction band. Okay, that is what is given here. You can see here. So the newly formed electrons are minority carriers in P region. So they freely move across the junction. Similarly, in the N region, you have holes formed, and electrons and holes, they move in the opposite direction to produce the total amount of current. So this gives rise to a photovoltaic voltage across junction. It is called as open circuit. When you don't connect any load to your photovoltaic cell or solar cell, it is called as open circuit voltage. Remember that open circuit means current is zero. Why current is zero? Because I don't have any load. So this is about 0.6 volt, which is developed by a single solar cell. So the amount of power the cell can deliver depends on its surface area, active surface area. So average cell can produce 30 milliwatt per square inch of surface operating a load of 4 ohms. So a single cell can produce 0.6 volt. So if you want more amount of voltage to be produced, you have to connect many solar cells in cascade. So average cell you see 30 milliwatt it can provide per square 1 square inch of solar cell. If you connect a solar cell in 1 square inch, it can deliver 30 milliwatt of power operating a load of 4 ohms. Okay, to increase the power output, you have to connect them in series and parallel combinations. So definitely you have to have them in series and parallel. Series combination means you're going to add them. Parallel means in order to make the voltage same. If you're having four rows of solar cells, and if you want to make all the four voltages coming from the cells to be uniform, then you connect them in parallel. So you follow series and parallel combination to improve the efficiency of the solar cell. So the efficiency is how much amount of electrical energy. Efficiency, it is output by input, right? So output is electrical energy, input is light energy. So the efficiency is given by electrical energy output by light energy input. The efficiency of any device you can find using the formula output by input, right? So here also we are doing the same things. Output is electrical energy, input is light energy. And at present, the efficiency has been found to be 10 to 40 percentage. So the efficiency of solar cell has been 10 to 40 percentage, and it is very, very low because majority of the uh, energy is wasted in the form of heat. So you cannot avoid that. So a solar cell is maximum. This is theoretical. 10 to 40% is theoretical. Theoretical now, which is not existing in practice. So when you physically fabricate these solar cells and see, the efficiency will be very much less than 40 percentage. So mostly we are using silicon and selenium cell because of their excellent temperature characteristics. We don't use germanium because output voltage from germanium solar cell is very, 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 very low when you compare to silicon and germanium. It is almost 5 times lower. Okay, it is one by, if the we have seen, right, if silicon is producing zero point 0.5 volt, means germanium is producing only 0.5 or 0.1 volt. So it is almost 5 times lower than silicon and selenium. So for solar cells, I will not be using germanium. I'll be using silicon and selenium. Two reasons: output voltage I get is very, very high. Second, the temperature stability is very, very good in silicon and selenium. So that is the reason why we go for uh, those materials for fabricating your solar cell. So both are going to be, see, photovoltaic cell and solar cell, there is nothing much difference, only in the construction and how we are going to take out the electrical power. So in photovoltaic cell, it is going to be voltage. We are going to measure the output voltage, but in the solar cell, I'm going to measure what is the output electrical power. That is the major difference. Nothing else. The operation, everything is going to be same.